All right, this is the Unit 9 test review number 19. This is the second gas stoichiometry problem on here. Given the combustion reaction C3H8 plus 5O2 yields 3 CO2 plus 4 H2O, how many liters of carbon dioxide can be produced from 1 liter of oxygen at standard temperature and pressure? Now remember, just like on number 18, I said there's sort of two ways that you can go about these gas stoichiometry problems. You have two options. You either are given enough information to where you need to find your number of moles first and then convert, or you're going to have to convert first and then work the gas law, the ideal gas law. So let's see what we're given in this problem so we can figure out which way we need to go. All right, so it asks us how many liters of carbon dioxide. So there's our question, that's what we're looking for. And we've got 1 liter of oxygen at standard temperature and pressure. Okay, so the first thing that we need to do is go ahead and get these givens down. So we know our volume of oxygen is 1.00 liters. We know that the temperature is 273 Kelvin, and we know that the pressure is 1 atmosphere, because that's what standard temperature and pressure is. And if you don't remember that standard temperature and pressure, you can look it up on your formula chart because it's written right out on the formula chart. Standard temperature and pressure, STP in parentheses, and it says 0 degrees Celsius and 1 atm. 0 degrees Celsius on the very next thing we know is 273 Kelvin. So, all right, there's our givens. We know that we are looking for the volume of CO2 in liters. Okay, now before we can get that, we are going to also have to find the number of moles of O2, and we're going to have to find our number of moles of CO2 so that we can convert. Which we can do in one step in the conversion problem. All right, so this we are going to actually do second. We're going to have to find our number of moles first using the ideal gas equation. So the first step is to use the ideal gas equation, or Pivnert, and remember we're going to use that to find the number of moles of oxygen. And then once we have that, then we will do our conversion, where we're going to go from moles of oxygen into moles of carbon dioxide, and then from moles of carbon dioxide we will go into liters of carbon dioxide. Okay, so we need two equivalent statements. The mole-to-mole ratio, remember, comes from our balanced chemical equation. So if we look up here at our balanced chemical equation, carbon dioxide is 3 moles for every 5 moles of oxygen. So we know that we have 5 moles of oxygen for every 3 moles of carbon dioxide. And then the relationship between moles of gas and the liters is off of your formula chart. The volume of an ideal gas at standard temperature and pressure is 22.4 liters per mole. We know we're at standard temperature and pressure, so we can use that. So that means that 1 mole of CO2 is equal to 22.4 liters of CO2. So that's what we'll use for the second equivalent statement. All right, so let's go ahead and substitute in here and get our numbers. So our pressure is 1, our volume is 1, we're looking for the number of moles. Oh, I forgot to write down our ideal gas constant for this. Since we are using atmospheres, our ideal gas constant is going to be the 0.0821. And remember, that's liters, atmospheres per mole Kelvin. I apologize, I forgot to write that down. You always realize it when you go to start plugging stuff in that you don't have a number written down up there. 0.0821 is our gas constant, and our temperature is 273 Kelvin. Alright, so solving then, 1 times 1 is just 1, and then we need to multiply the 0.0821 times 273. 0.0821 times 273 gives us N times 22.4133. So to solve for N, that means we need to divide both sides by 22.4133. So that means that N is equal. Okay, so N is equal to 0.044616, and that should be enough. You need to make sure you take it out a few places so that you don't have error. So remember that this is your moles of O2. Alright, so at this point now we can compare and do our second step for our solution, which is plugging into our conversion statement here, or doing our stoichiometry. So that means that we have 0.044616 moles of O2, and then we use our first equivalent statement, the mole to mole ratio. So that means 3 moles of carbon dioxide is equal to 5 moles of oxygen. So 3 moles of CO2 over 5 moles of O2. And then we're going to use our second equivalent statement to go from moles into liters. So 1 mole of carbon dioxide is equal to 22.4 liters of carbon dioxide at standard temperature and pressure, which is what we're at. Any gas, the volume is 22.4 liters for a mole at standard temperature and pressure. So 22.4 liters of CO2 is equivalent to 1 mole of CO2. Alright, so math-wise, what do we need to do here? We need to take our 0.044616, multiply by 3, divide by 5, then multiply by 22.4. So let me just write that down, that's what we're doing for our solution here for the second part. So we're taking 0.044616, multiplying by 3, dividing by 5, and then multiplying by 22.4. So when we do that on the calculator, 0.044616 times 3 divided by 5 times 22.4 gives you 0.5996. Alright, and then we need to look at our significant digits. So up here we've got 3. Remember the ATMs is exact. And then our constant is 3 as well, which means our answer needs to go to 3. So the 6 rounds the 9 up, which rounds the 9 up, which rounds the 5 up. So our final answer for a volume of CO2 is 0.600 liters. And that is the final answer.